Hello, everyone. Today we are going to discuss the remainder of the uh, parts of the circuits, diode circuit rectifiers. So, if you remember in the last class, we discussed the half wave and the full wave rectifier circuits. And we said that if we add a capacitor, this is going to make filtering. So let's go more in deep today and discuss about this point filter and how this capacitor is going to perform smoothing for the voltage in our circuit, and how can we size this capacitor and calculate the ripples and improve the performance of the rectifier circuit by means of this capacitor. So let's start from this point again. So we covered this part very quickly last time, but let's go more in deep today and discuss it in more detail. So now the idea of the capacitor, guys, is the capacitor is a storage element. So what the capacitor is doing in our rectifier circuit. So during the positive half cycle, if this diode is turned on, so what will happen is the volt here, if this capacitor is not charged in the beginning, so it has firstly 0 volt, nothing, no charges on the capacitor. So what will happen is when the volt at the anode side is greater than the volt at the cathode side, which is theoretically equals 0 in the beginning. So this means in the positive half cycle, once the volt at anode side is greater than 0 at the cathode side, or let's say exactly greater than the turn on volt, let's say 0.7 for instance. So in this case, this diode will be turned on. And once the diode is turned on, so this is going to be our circuit. So we will have a DC supply, we have a capacitor, and our load is connected here. So this is now our circuit. So the current is going to flow here to charge the capacitor and supply the load at the same time. So we will have now here current moving in the capacitor, current at the load side, and this is the supply current, which is the same as the diode current. Okay, and this is our supply volt. So let's move it step by step. So once the supply volt, this red color, supply volt is increasing and more than 0.7 volt, the turn on volt of the diode. So in this case, the capacitor volt here will be nothing but Vs minus V diode. So if we say V diode is, assume that V diode is 0.7, so we can say now V capacitor equals V source minus V gamma, or V turn on, which is 0.7 for instance. So this will be the shape now. The capacitor volt will increase until reaching to the peak value. So without capacitor, we used to have current multiplied by resistor. So the cathode volt here will be following the current, which means the volt will reduce according to the sinusoidal waveform. However, because we have a capacitor here, what will happen is, once you have a capacitor, so this diode will be, or the volt across the capacitor will start decreasing to a certain point here. At this point, guys, as you can see, the capacitor volt equals the supply volt, which means now if the capacitor volt equals the supply volt, or even the capacitor volt is less than the supply volt by the magnitude of V gamma, so this means now the volt here is equal, which will try to force this diode to be turned off. Theoretically, the diode will be turned off if the current reaches 0. Okay, but let's assume now, according to the voltage waveform, what will happen is the volt here is going to be equal, and this means the diode will be turned off and the capacitor will start charging, or sorry, discharging the stored energy in the connected resistor. So this is what's happening here, guys. So we can assume that this is the waveform of the capacitor now. And since we have only C and R, so we can assume that this waveform is exponential waveform, and the capacitor volt in this period is going to be V equals alpha times e to power minus t over RC. What is RC? RC actually is the time constant of the circuit, which represents the capacitor and load resistance. And this is a first order differential equation, so it can be calculated in order to know exactly what the value of alpha. So this is now expected the waveform we will have for the capacitor volt. And you know the capacitor volt is connected to our output, so we can say this is going to be the output volt. When this diode will be turned on again, this diode will be turned on if the volt at the supply side here, the anode volt, became greater than the volt across the capacitor by the value of turn on volt. So in this case, the diode will be started again and conducting the current again. And if this happens, the capacitor will charge again and this cycle will be repeated. So this is the concept now of having capacitor. You know, guys, the amount of energy stored in a capacitor depends on the voltage and the capacitance value. So energy equals half CV squared. Okay, I think all of you know that energy of a capacitor equals half times CV squared. So if you have high value of capacitance, so this means you can have high energy. And this high energy or the high stored energy will allow the volt to stay longer. It will not dissipate the volt fast. And this will be very clear from mathematically because of the time constant. So if the value of C is relatively high, so in this case, RC will be high, which means the capacitor will not discharge quickly. And this is required here because if you imagine that this volt is not going to decrease quickly, so it will take longer time. And this means now the volt will not drop to 0 and will continue with higher values, which means in another way, or let's say technically, we say with less ripples. So what the meaning of ripples? So we will see this together in the coming slide here. So as you can see here, guys, this is now the operation at steady state. So the first operation or the first part here, we could see in the previous slide. So this is in the transient period. Transient means if you don't have any initial condition, capacitor firstly was not charged, it's still in the beginning. So this is called transient part. After the transient part, you will have a steady state part, which means this part here represents the capacitor volt while discharging. And at this point, which is referred to here as VL, at this value of volt, here the capacitor volt became equal to the supply volt. So this means the supply volt is going to be higher than the capacitor by the amount of turn on, and this will turn the diode on again. And if the diode is turned on, this means the supply volt will charge the capacitor, so the capacitor volt will increase again until reaching to the maximum value. And the maximum value is nothing but the supply volt minus V gamma. And once we reach again to this point, so what will happen? What will happen is the diode will be turned off and the capacitor will continue discharging until the next half cycle. So this is a concept now, guys. At steady state, guys, and assuming a exponential relation for the volt like that, so we can find that V out, which is the capacitor volt, equals Vm times e to power minus t prime divided tau. Okay, and t prime means the time starting from the instant of this point. Because if I say t, so t means starting from t equals 0. But the waveform is representing the volt starting from this point till this point here. Okay, we don't need to have the other part of the volt here from this point to the maximum because it's a part of sinusoidal wave. So this is going to be the same as the sine wave supply. Okay, so we can say the voltage equation will be this equation from this point to that point, and the remainder time here will be the sinusoidal supply. Will be the same as the sinusoidal supply minus the turn on volt across the diode. So this represents, guys, the equation of the capacitor volt or the output volt. Okay, now, since this is our waveform, guys, we do prefer the circuit to have less ripples. So this is one of the, we call it quality. So if you have high quality supply, in order to have high power quality, we need to have less ripples. Less ripples, what the meaning of ripples and how can we calculate ripples? Let me firstly say if I have half wave like that. Ripples means the maximum volt minus the minimum volt we have here. So the maximum volt here in this waveform, guys, is going to be the maximum. And the minimum volt here is 0 volt. So this means here the ripples equal the maximum. But this is in absolute value or measured in volt. If you would like to calculate ripples in percent, so we can divide these two or normalize the value in order to get it in percent. And the normalization is going to be to the maximum volt of the supply. So this is called ripple. So the ripple in case of half wave rectifier without filter is the maximum. In our case here, once we have capacitor, the ripple will be between the maximum and minimum. So it's V maximum minus VL. Okay, so this is the relation. V maximum minus VL will represent the ripple volt. How can we calculate this value? So from the equations, guys, so in the previous slide, we said this is the equation we have. This is V out of 2, V maximum e to power minus T prime divided tau, which is RC. And we can get the value of VL from this equation. How? Simply at this instant. So this is the equation now. We started from the maximum value until this instant at T prime. So if you substitute at T equals T prime, this means the value of V out of T will be VL. So we can say now VL equals V maximum times e to power minus T prime divided RC. Okay, guys. So this is now the equation of VL. If you subtract V maximum minus VL, it will provide us with the ripple voltage equation. So we can say now V ripple equals V maximum minus VL. So this is going to be 1 minus e to power minus T prime divided RC. Okay. Now, Regarding this interval, guys, e to power minus t prime divide RC, if you assume the linearity of this part of the equation, so we can say this is equivalent to 1 minus t prime divide RC. So this is mathematical approximation. So once we have the value of t prime much less than RC, so in this case, we can say this part of the equation equals 1 minus t prime divide RC. So if you replace this in our equation here, so this is going to be now the V ripple will be approximately equals V maximum times t prime divide RC. And to be honest with you guys, the part of t prime is very close to Tp, which is the time to reach to the maximum value again, if you have less ripples actually. So we can assume that, just for simplicity, we can assume that t prime is almost equals Tp, and then in this case we can say ripple volt is approximately equals to V maximum times Tp divide RC. So this is approximated solution now. Okay. And Tp is going to be the period of our cycle. Okay, so it's 1 divide the frequency. Sorry, Tp is period of our cycle in the full wave, which means it's going to be 1 divide twice of the frequency. Okay. Nice. So now we can say V ripple equals V maximum. Tp is nothing but the time of half period. So 1 divide the complete period, or 1 divide 2 of the complete period, or 1 divide 2 times the frequency. So we replace Tp here by 1 divide 2f, and then we multiply times RC. So this is now the relation. V ripple equals V max divide 2f RC. In terms of design, guys, we mentioned this in the last class. Frequency is nothing but the supply frequency. You don't have access to change the supply frequency. And you may not have access as well to change V maximum. This is the supply coming to your home or to the device you would like to design a rectifier. So V maximum and frequency are supply dependent, and we may not have access to change any of these parameters. Regarding R is nothing but the load seen by the rectifier. So whatever load we have on the rectifier, it will have effective or equivalent resistance. So this equivalent resistance also load dependent. We don't know what will be applied to your load, so you have no access to control R. But the only thing you have access to control here is the capacitance value. So we can say, guys, V ripple is inversely proportional to capacitance. If you would like to reduce the voltage ripples, if you would like to reduce the ripple voltage of your rectifier, and this is appreciated, this is recommended, so we can increase the capacitance value. But for sure, guys, every design has some limits or thresholds. So we will see together now some numerical examples. How can we make sizing for a capacitor in order to limit the ripples to a certain amount? You cannot, so the ideal is having 0 ripples. But we mentioned before, ideal is something impossible. We don't have something ideal in our life. So you have to have some ripples. And also, cost-wise, you will not increase the capacitance very much because the cost will be very high. So you have cost limitation as well. So we will see together now, guys, how can we make sizing for this capacitor. But let's read the note we have here. So here, guys, as we mentioned, TP, guys, is the half period time. Okay, so we replace it by 2 frequency. So the factor 2 we have here shows that the full wave rectifier has half of the ripples voltage of the half wave rectifier. How it comes? Actually, because in case of half wave rectifier, we don't have this part of the cycle. So this is only for the full wave rectifier. For that, guys, if you have half wave rectifier, the waveform will be different. So this is in case of full wave rectifier. In case of half wave rectifier, so the factor 2 here will be removed. Okay. Okay. Let's solve this example together. So here, we need to determine the capacitance required to yield particular ripple volt. So this is called, guys, design requirements. We need to have a rectifier with a certain desired value of ripples. So let's see the example here. Consider a full wave rectifier with 60 hertz supply input frequency and signal and peak output voltage is 10 volt. So the maximum volt is 10 volt. Assume that the output load resistance is 10 kilo ohm. The ripple voltage is to be limited to VR equals 0.2 volts. So here in this example, it gives 0.2 volt as a maximum or as a limit or constraint for your design. So how can we design this circuit? So you know that our relation, we just mentioned that V ripple equals V maximum divide 2 frequency RC. So this is our relation. So simply we can get C and move VR here in the denominator and move C here in the left-hand side. So we can say C equals V maximum divide 2FR V ripple. So this is going to be now 2 times 60 hertz times our resistance is 10 kilo ohms. So 10 times 10 to the power 3 times ripple volt, 0.2 volt. So this is going to give us this capacitance value, 41.7 microfarad. So this is, guys, the capacitor needed in order to limit the ripples to 0.2 volt. Okay. Before moving forward, I have comment here on this example. And I have also something to discuss with you regarding the capacitor specifications. Firstly, guys, I'd like to see how much percent ripples we have here. So in order to know that, let's calculate the ripple volt we have here. So 0.2 compared to V maximum, or let's say V output, because V output is going to be your maximum volt. The required is to have V maximum equal 10 volts. So if we say now, guys, 0.2, or let's say V ripple in percent of V maximum equals V ripple divide V maximum times 100%. So this is going to be now 0.2 divide 10 times 100%. If you calculate that, 0.2 divide 10, so this is going to be 2%. To be honest with you guys, we do prefer to mention the ripples in percent, not in magnitude. So if I'm going to say the ripple volt is 2%, this means the quality is relatively good. If I can say voltage ripples is 5%, it's still acceptable. But if I'm going to say the voltage ripple is 0.1%, this may cost us a lot of money. Let's calculate this together, guys. I'm going to assume now that I need V ripple percent equals 0.1%. So this means I need VR to be 0.1% times our V maximum. So this is going to be 0.1 times 10 divided by 100. So this is going to be, guys, 0.01 volt. If we substitute here in our relation to calculate the capacitance, so let's say C number 2. So this is, let's say this is case number 2. And the first one here is case number 1. So for C2, guys, and this is VR 2%, VR2 equals 0.01 volt. So let's substitute here in the relation, guys. So we have V maximum 10 volt, 2 times 60 hertz times 10K, which is 10 to the power 4 now, times the V ripple, which is 0.01. So let me calculate that on my calculator. 2 times 60 times 10,000 times 0.01. So we have a capacitor of 833.33 microfarads. Okay, so this is the capacitance value. Now, in terms of cost, if this capacitor price will be the same or close to this capacitor price, actually, it depends on some other factors. It's not only capacitance. It depends on the voltage as well. And this is moving us to the next question. How can we specify a capacitor? So in order to specify a capacitor, you need to specify the capacitance value, how much farads you have, and the voltage magnitude. Besides that, also frequency. If you are going to use a capacitor for very high frequency, so you have to specify frequency as well. But for our applications, let's consider now the capacitance and volt, because this is going to be applied to DC circuits. So, and the frequency is 60 hertz only. So we don't have high frequency in the rectifier circuits for the time being. So if the volt is relatively high, guys, let's say 100 volt capacitor, for instance. So this difference may make the price tripled or maybe 4 to 5 times also. Okay, so it's gonna cost a lot of money for getting this, in order to get this high capacitance value. And to be honest with you, it's not that important to reach to the volt to be just 0.1%. It's not that critical. So 2% is fine, 1% is fine, but 0.0 or 0.1% is relatively high. Okay, so we need to make all of the time, guys, in design, we need to make balance between the quality and cost. Okay, because by the end, every product will have a certain price, and you know, in the market, you will have a lot of competitors. So you can compete with quality and price. If you have something with high quality, and at the same time, the price is reasonable, not very expensive. So this will allow us to produce more and sell more of your product. So this is a target in markets. So this is an example. How can we make sizing for our capacitor? Another part, guys. In this example, the load is defined here. So the resistance here is 10 kilo ohm. What if you have a rectifier connected to a load with unknown resistance? And we will see this together in our lab. How can we make sizing without knowing the resistance value? So in this case, you have to find the equivalent resistance seen by the rectifier circuit. So this is the way. So R here means the circuit resistance seen by the rectifier. So if you have supply, AC supply, and here you have a certain rectifier circuit. So this is a rectifier. Any resistance connected here is called R effective or R load. So you need to get the R effective seen by the rectifier. How can we do that? You can use any circuit analysis technique. Definitely, you know, Thevenin analysis. So once you get the current output and the voltage here, so you can get R effective as V output divide I output. So this is going to be your effective resistance. And by this way, you can make sizing for your capacitor. So this is also one important thing you need to understand, because you may not have your load resistance given in reality. But in numerical problems, as you can see, it's very easy to give it as a given data in the problem. But in reality, you may need to calculate or to estimate the load resistance in order to calculate the capacitance needed for your rectifier. As we mentioned, guys, in our lab yesterday, simulation is very important in order to make sizing and design. So here we will have the example, the same example we solve it now, and we will see the results if we make simulation on PSpice with and without capacitor. So this is a circuit before of inserting a capacitor. We will see together the performance of the circuit. And then after adding a capacitor of 41.7 microfarad, what will be the performance of our rectifier circuits. So this is the first case before of adding capacitor. So what you can see here is we have the supply volt, this purple waveform, and then we have the green one here represent the output volt. So this is the output, the green one. This is the supply. And sorry, it seems like the current is the green one. The current. So this purple one is the supply volt, and we have the volt across resistance. Okay, yeah, the volt across the resistance, guys, is just these triangles here. So it's the same as the green one. So the green one is also the current, the circle greens. This is also current. Why we have identical waveform for the current and volt? Because actually it's not given to the same scale. So we have two scales here. But if you have just one vertical X, you will have two different waveforms. But since we split the voltage and current axes, so the PSpice plotted the two curves as just one curve, okay? Because you know that I and V across resistance are in phase all of the time, okay? But for sure here the peak values are different. So this here represent, for instance, like around, let's say, 0.9 something milliampere, and the green one here will represent 10 minus the turn on volt of your diode. So as you can see here, guys, I expect this may be like 0.7 volt, for instance. So this is a voltage drop across our diode, and the last curve here represents V across diode. So this curve here represents the V diode. V diode means V anode minus V cathode. So during turn on, you will have a volt, which is the turn on volt here. And during turn off, this will be the turn on volt. So if I draw the circuit here, so the circuit again is we have our AC supply, we have one diode, and a resistor like that. So this means during turn on, this diode will have only V on, and during turn off, this diode will be open circuit, which means the volt of anode is V supply, and the volt of cathode is V output, which is going to be 0 during turn off. So this means the V anode to cathode will be the same as the supply volt. So this is the peak of our supply volt, which is 10 volt. So could you see, guys? This is how can we understand the waveform. So you have to analyze the waveform in order to understand the concept by this way. Okay. Okay, great. So this is the case before of adding capacitor. Let's add a capacitor here and see what will happen. Let's take it step by step now. So firstly, unfortunately, the waveforms are not defined here in this screenshot, but we can recognize the waveforms from our understanding. So this is here, guys, represent the capacitor volt or V out. So this is V out or V across capacitor. As you can see, you have a difference between the peak value of the supply volt. So Vs is the green one. So this difference is nothing but the turn on volt of your diode. And current is not plotted here in this curve. But as you can see, guys, we have this volt here. What's this volt? Actually, if you have a look at this period, so we can say this is the turn on volt, which means this is V diode now. Until this instance, can you see, guys, this instant here, if we move a vertical X here, will be this point. So can you see, guys, at V diode equals 0, V capacitor equals V supply. This makes sense. So once V supply became equal to the capacitor volt, the diode volt turned to 0 because the diode will be turned off, and V diode will be, V diode is nothing but V anode minus V cathode. So it will be V supply minus V capacitor, V cathode, and V cathode is nothing but the capacitor volt. Assume that the capacitor volt is going to be constant. So if we neglected the ripples, so assume we neglected the ripple, so this volt magnitude now, if we neglect completely the ripple, so this volt is going to be 10 minus V gamma. Assume V gamma is 0.7, for instance, so this is going to be, assume 9.3 volt. So we have 9.3 as a capacitor volt. And we have the supply volt here. So I'm going to say this is V cap and assume V cap is 9.3. So in this case, guys, if the supply volt became minus 10, which is minus V maximum, the capacitor volt, can you see the value here? It's going to be minus 10, minus 9.3, so minus 19.3 volt. It was different in case of the circuit without capacitor. So if we go back here, this is the diode volt. So the peak inverse volt here in this circuit equals 10 volt. But in case of adding capacitor, the peak inverse volt of our diode became V maximum plus V cap maximum. V cap maximum. And if you neglect ripples, I'm going to say V cap maximum, which is approximately equals V maximum if you neglect the turn on volt. So this means, guys, in case of capacitor, you should size the peak inverse volt of your diode to twice of the maximum. Otherwise, the diode will be burned. So this is very important note. If you have capacitor filter in your circuit, the diode peak inverse volt has to be 2 V maximum. Sorry, this is the diode peak inverse volt, not breakdown volt, okay? I'm not sure if I said breakdown or peak inverse. So the diode peak inverse volt is 2 V maximum. But when you specify a diode, you need to get a diode with a certain breakdown volt. So V breakdown, guys, has to be greater than peak inverse volt. And we should assume also a safety factor. So if I'm going to design such a circuit and I have 2 V maximum equals 20 volt now, so I'm going to say get V breakdown approximately equals 1.5 times 2 V maximum. What is 1.5? It's just a safety factor. Because you don't know during switching or during anything what may happen. You may have like any kind of overshoot or anything in your waveform, and this may damage your diode. So you have to consider safety factor at least 50% for the power electronics and the electronics application. Okay, guys, so this is how to make sizing for the diode in case of using capacitor in your circuit. But what about the capacitor volt? Actually, as you can see here, the capacitor volt is going to be rated at V maximum of your supply. So if your supply volt is 10 volt, so the capacitor volt is going to be 10 volt at most. But again, you should consider some safety factors. So select capacitor volt to be like, for instance, 20 volt. You may not find 15 volt capacitor, okay? But if you have relatively high power application, so if you have, instead of 10 volt, assume that, for instance, for the 110, so if you have V root mean square equals 110 volt, so this means V maximum will be 110 times root 2 1.4 something. So this is going to be, let me give you the exact value. So 110 times root 2 equals 156, almost 156 volt. So if you are going to use a rectifier connected to the home supply, the capacitor volt is expected to reach to 156 volt. So don't use capacitor less than 200. You have to consider some safety. Okay, guys? So this is how can we make safety factor, or how can we assume and select the capacitor. Okay, and the same is also for the diode. So since the peak volt of the supply is 156, so 2V maximum will be, in this case, 311 volt. So use diode with at least 400 or 500 volt in this case. You may not find 400, you may find 450 volt. So in this case, we may select 450 volt or 500 volt diode in order to support the maximum peak reverse volt you have in your circuits. Okay, guys. So now, for this circuit, for the rectifier circuit with the capacitor, we made sizing for two parameters. The capacitor as a filter and the diode as the main rectifier element. Okay, nice. Very good. Now, if you zoom in the capacitor volt to see exactly how much ripples we have. So as you can see, guys, this value is 9 volt, the minimum value. The maximum value here is given at this cursor. So I'm not sure if where is the cursor in the, yeah, so this is the first cursor. The second cursor is not clear to me where is the second cursor, but assume this is a one. Okay, so this is the cursor here. So this is the cursor of y. So you have 9.33. So 9.33 maximum. This is the maximum value. And this is the first minimum value. So you have now 0.33 volt ripples, 0.33 volt or 0.34 volt ripples in this case. Okay, if you use the 41.7 microfarad capacitor. Okay. In the example, by the way, it was 0.2, correct? We have here 0.3 something. So it's not exactly like what we have in our theoretical calculation. We have a difference now in the voltage ripples. Okay, so if we go back here again, so the voltage ripples with this capacitor value was 0.2 volt, but here we got 0.339 or 0.4 volt. So it's not the same. Why it's not the same? So you need to think about it, and next class we will discuss it together. Or next lab we will discuss it together. Okay, guys? So why we have difference between the simulation results and the theoretical results, we need to discuss it in our next lab, not class. Okay. Now, if we use twice of the capacitance value, so here, as you can see, guys, I increase the capacitance value to 83.4 microfarad, and we got the minimum volt is 9.13, the maximum volt is 9.3, so the difference is around 0.17 volt. So this is the difference here. So 171 millivolt. Okay, so this means, guys, as we discussed, if you increase the capacitance value, the ripple volt will decrease. I think let me check if we stayed longer than the class time. I think we still have time. Okay. Now, let's see, guys, the diode current in this example. So we already added a filter, and we have now diode. This diode is conducting for part of time, and we need to make sizing for this diode. So in order to size a diode, we firstly figured out the voltage and how the capacitor affected the volt. But now regarding current, because if you would like to specify a diode, you would like to buy a diode from the market, so you need to specify also the current. So let's see together how can we specify and calculate the current of our diode. We agree together, guys, that in this period from here to here, the diode is on. Other than that, our diode is off. Okay, so according to the current, so if you find here the I diode, so you can say I diode equals I load plus I capacitor. I load, IR plus IC. Okay, so you will find this is the shape of the diode currents. For sure, guys, the diode will be turned off once the diode current reaches 0. And as you can see here, this is the diode current reaches 0 at the instant of turning off. And this was the current value at the starting. Okay, so this is now the part of or the current waveform we have during the diode turn on. How can we express the current? So let's make it step by step. So we agree together that I diode equals I capacitor plus I load or resistor load current. You know that for any capacitor current, guys, IC equals C dV by dt. So this is nothing but the capacitance times the output, which is the same as the capacitor volt, divide dt, plus the load current. And the load current is nothing but V out divide R. So now we have the equation I diode equals C dVO dV out by dt plus V out divide R. So this is the diode current equation. The peak diode current for a full wave rectifier can be calculated by this equation. From where, guys, we got this equation? Actually, this is a differential equation. This is a first order differential equation, okay? And the solution of this differential equation will be, as you can see here, so we have here the ID peak value equals 1 plus pi times 2V maximum divide VR. And this is the peak value, and this is the average value. So we don't have here the complete equation, guys, but just the peak value and the average value of the equation. So the revision is not required here, okay, because it's relatively complex. So what we can do is just using these relations, if you'd like to solve problems with these relations, so you can add it in your formula sheet, okay? So again, the diode peak current is V maximum divide R times 1 plus pi square root 2V maximum divide VR. And the average value of the diode current, you know that for any waveform, if you'd like to get the average value, it's nothing but the integration for a complete cycle. So this will be 1 over pi times 2VR divide V maximum times V maximum divide R times this part of the relation, 1 plus pi divide 2 root 2V maximum divide VR. So again, you don't need to drive this equation. It's relatively complex, okay? However, we can use it in examples or in problems. And again, guys, this is going to be a part of the current. And here, this is a direct example for the calculation. But I have a different concept. Okay, I have a different concept. What is this concept? If you sized your circuits according to these values now, definitely this diode current average value will be less than the value of the diode current if the capacitor is not here. Why? Simply, if you go to the circuit without capacitor, say for the simple half-wave rectifier, okay, let's have it also for just the resistive load, like that. So what can you see here, guys? The diode current is the same as your load current, correct? So in our circuit, let's go back again to our circuit. What will happen if your capacitance is broken? Or due to any problem, it's not working anymore in the circuits. In this case, this is going to be open circuit. So if the capacitor is not Here, this is going to be open circuit, and the diode current will be the same as your load current. So in the design, guys, you have to consider the worst case scenario. So practically, I do prefer to consider the worst case scenario, which is the capacitor is not working, and the diode current is going to be the same as the load current. So this will be for sure high value of current compared to the diode current in this case. Why I'm assuming that, guys? Because the capacitors, you know, guys, we have so many types of capacitors. One of the types of capacitors is called electrolytic capacitor. The electrolytic capacitor is relatively cheap, and it exists in a lot of products. And the lifetime of this capacitor is very small, like 2 or 3 years at most. If the capacitor is broken, just the lifetime, okay? So you should reserve yourself for the diode. Otherwise, the diode itself will be burned as well, okay? So I do prefer not to consider the case we have here, but consider the worst case scenario. So the worst case scenario is I'm going to size the diode according to the main load current. Okay. So this is the concept of the design. Okay. And this is what I do prefer to make in such cases. Okay. Here, guys, we have a design. So we need to design a full wave rectifier to meet particular specifications. So let's see what are the specifications needed. Full wave rectifier is to be designed to produce a peak output volt of 12 volts. So the output volt is required to be 12 volts. And deliver 120 milliampere to a load or to the load. So this is the current needed, and this is the voltage needed from our rectifier. And produce an output with a ripple of not more than 5%. This is a practical example. Why I'm saying it's practical? Because it didn't say I need a certain voltage magnitude for ripples, but 5%. 5% is a reasonable value or reasonable percent in terms of power quality factors, okay? So we need a 5% ripple, but not 5%, not more than 5%. So if you make it 4%, it's fine. If you make it 3%, it's fine, but it's going to be according to the cost. So it will cost you more money, okay? So this is the way, guys, how the customers doing call for products in the markets. So they require certain like constraints like that, and they got offers or quotes from the different companies. So for sure, if a company produce or provide a quote with higher quality and less price, so this will be selected. This definitely will be selected. There are some other political issues also, but let's say engineering-wise, consider the two factors, which are the cost and quality. Okay. So in terms of cost and quality, the higher quality with less cost will be selected. Okay. So if, for instance, someone provide me with this rectifier with the same required volt, 12 volt, 120 milliampere, and the voltage ripple is 5%, but it will cost me like $10, and someone else say it's 4% and cost $10, so for sure I will select the 4%. So this is now the competition between companies in the market, guys. So consider the quality and price. Okay. So now we need to make a complete design for this rectifier. And he said here it's full wave rectifier. Sometimes, by the way, it may not be required or may not be like given which circuit you should use. So it's up to your capabilities and based on your design, you can use full wave, half wave, whatever, but we need to have some constraints. So achieve the constraints to me, give me the desired values, whatever the circuit you have inside, I don't care. Okay, but here he defined we need a full wave rectifier. Okay, so let's start from our load side, guys. So firstly, we know that we need 12 volt and the current is 120 milliamperes. So 12 divided 0.12 is 100 ohms. So this is the resistance. So we will use this resistance in our sizing. Assume that the diode cut-in volt is 0.7. For sure, it depends on which diode will be selected, and you can get this diode turn on volt from any diode datasheet. The peak value of the volt Vs in this case, guys, will be for sure 12 V out maximum plus 2 times V gamma. This is according to our discussion about the full wave rectifier before. We said that you have 2 diodes connected in series. So this means 2 V gamma plus V output maximum will provide you with a supply voltage maximum. So Vs maximum is 13.4 volt now. So this is the maximum supply volt you need. For a sinusoidal supply, you know that the maximum value is RMS times root 2. So in order to specify or get a transformer, you need to specify the RMS volt. So we can say now VRMS equals V maximum divided root 2, which is 9.48. So this is now the secondary volt of our transformer. So we have now transformer which will supply our rectifier circuit, and we need here 9.48 volt. And any volt, guys, in AC is RMS. Any volt given in any data sheet or anything is the RMS value. We do not specify sinusoidal waveform by maximum value or peak value. Okay, so this is the secondary volt now. We need to get the turns ratio required in order to get the 9.48. So assume that we have a supply of, or sorry, not assume, it's already given. So the supply is 120 RMS. So we have here 120. So we can say now N1 divide N2 equals 120 divide 9.48 in order to calculate the turns ratio. So we got that turns ratio is 12.7. So you should specify or get the transformer with this turns ratio or the closest value to this turns ratio. This is for the transformer part. Let's see the capacitor sizing. So we need to have 0.05 of Vmax. This is the 5%. So 0.05 times V maximum is 0.6 volts. So this is ripple volt we have. Simply, you can use the relation now. You have V out equals 12, frequency equals 60. The resistance is 100 ohm. Ripple volt is 0.6, so you can make sizing for your capacitor. So the capacitor is 1667 microfarad or 1.6 millifarad. Okay. Now, we made sizing for the capacitor. We need to get the diode current. This is the way I just mentioned to you guys. I dislike this way. So this is the textbook solution. In my, let's say, strategy of design, I do prefer to consider the average current of your load to be the same as your diode. Don't consider the peak value or average value in this case. So I do prefer, as I mentioned to you, assume that if the capacitor is not there, so in this case, you should consider the load, the load current, not the just the peak current. Okay, so substitute here in the relation, you will get the average value of current. Okay, so this is the average value, 132 milliampere. Yes, but one important thing here, guys, is the peak current. What's the peak current we have? So the peak current here is 2.5 ampere. Okay, so the peak current is 2.5 ampere. The ID average here is 132 milliampere. Okay. Finally, we need to get the peak inverse volt. So the peak inverse volt, we can get the peak inverse volt of our diode, as we mentioned. It's Vs minus V gamma. So this is going to be now 13.4 minus 0.7, so it's 12.7. So this is a peak inverse volt of one diode, For sure, you have two diodes in series in this circuit in order to reach to the 2V maximum. So this is the volt across one diode. Okay. Now, guys, this is activity. Please, guys, this activity need to be designed, but not for the coming class. This will be added after we finish the two coming labs. So this activity will be due on week number 6. Okay, I will post this on eCampus. So what we need to do here is design a DC power supply to supply electrical appliance that requires 5 volt, 1 ampere, and in your design, consider the following. The available supply is 110, 60 hertz. The power size limited to 10 centimeter times 5 centimeter times 5 centimeter. So this is a size we need. Don't increase the size over this value. Use voltage regulator 7805. So this is one of the techniques you need to have in order to make regulation for volt. We didn't discuss the voltage regulator yet. We didn't discuss the voltage regulation. Later on, we will discuss the Zener diode and the voltage regulators. So this is what will be used. And the design means specifying all parameters, values, and the safety factors considering during the selection of your elements. There is a hint. So the components needed in the DC power supply are step-down transformer, diode rectifier, smoothing DC capacitor, and voltage regulator. We already covered the first 3, but this one is not discussed yet, and we will start discussing this from the next class. This is what we need to discuss today. So this is a summary for the materials we have for the time being. And up till now, we covered these outcomes from our course outcomes, how to make calculation for the quantities of semiconductor devices. So we covered this for our diode, and describe the operation of diode, solve problems involving diodes. So we covered these outcomes now. Employ diodes in various applications. So we added this in battery charger before. We solved one example related to battery charger. We solved example related to transformer, and we covered some parts of power supply. We rectifier, and we solved some parts related to power supply as well. So these some applications. Also analyze diode and transistor. So we covered the diode for the time being using PSpice software, and these are the covered or the fulfilled outcomes for the part of the diode for the time being of the class. Thank you so much, guys, and see you in the coming classes. Have a good one.